I understand that this topic is kind of, how can I say, not so difficult. I think it is not so difficult, not so familiar. I mean, it sounds a bit awkward possibly, but I think it is essential if you are interested in serious financial engineering, and then if you want to study finance more in graduate school or study more. And so this topic is important for advanced topics in finance, and this topic is also important for if you are interested in mathematical theory about statistics, which is also basis of econometrics in graduate classes and those things. So I think this is important. So even though it is kind of difficult, I hope you can enjoy it. It is difficult, but I think it is fun. First topic is martingale, a stochastic process. For the time being, you can understand stochastic process, a series of random variables. You know random variable, right? What is random variable? Can anyone explain what is random variable? Bill, what is random variable? Anyone? So, even though you cannot specifically describe the definition of random variable, you have some notion of random variable, right? You heard of random variable. But anyway, I will provide you very mathematical, rigorous definition of a random variable later on. But just you have a brief idea about random variable, we can define stochastic process. So it is a series of random variable with a subscript of time. So like this, x1, x0, x1, x2, those things. So a stochastic process. And a stochastic process is called a martingale. Martingale, if it satisfies these two conditions. The absolute value of any random variable in the stochastic process, its expectation is less than infinity. It's called integrability condition. Expectation, mean, is basically integration. Okay, if we describe the calculus, is basically integration. So, if absolute value is less than infinity, it means we can calculate integration, which means we can calculate mean. So it's integrability condition. And second one is more important. First, technological part. Second one is given the history of a stochastic process from x0 to xn, and the expectation of next variable xn plus 1 is simply xn. Okay. So it is a condition, it's a statement of conditional expectation. If we know the information from x0 to xn, next period xn plus 1 is simply xn. So even though we have full information on the history of this one, actually we don't actually need information from x0 to xn minus 1, because given the information xn minus xn, the expectation is simply xn, right? So this martingale is important in finance. Why? Do you guess why? Is stock price martingale? How do you think? Stock price is not exactly martingale because there is a deep term. The stock price have, at least historically, stock price has a tendency of going up. Okay, going up. So it is not martingale. In this case, there is no drifting up. So not martingale, but in short term, like if you take a look at daily price, intraday movement of stock price, that is still not exactly martingale, but martingale is good approximation of the movement of stock price intraday, or like a daily stock price. Right? That's intuitive, because if it is not like this, of equity data, if you have information about the historical stock price, and if you have X and plus 1, next period stock price is different from stock price right now, then you can basically make money, right? If this is higher than this one, well, people think stock price will go up, so people take a long position on the stock. Right? If it is less than this one, if left-hand side is less than right-hand side, well, then people can take short position. In the very short time, the inventory cost, if opportunity of cost of funding is 0, right? In very short term, which is usually it can be usually approximated with the risk-free rate, but in the very short time, the funding cost is almost 0. Therefore, this should hold. Right? So this definition, this notion of martingale, is in line with efficient market hypothesis, especially weak form of efficient market hypothesis. Weak form of efficient market hypothesis says that even though given the information about the history of stock price, you cannot make money. Right? That's the definition of weak form of efficient market hypothesis, and this is exactly like that. You have a history of stock price. The best estimate of your stock price of the next moment is just stock price right now. Best stock price of IBM, your best guess about stock price of IBM 5 minutes later is IBM stock price right now. Something like that. So that's why martingale is very important in finance. And then we can slightly generalize this definition of martingale like this. Now we have two stochastic process, xn and yn, n from 0 to n, like this. So there are two stochastic process. By the way, here this stochastic process is discrete. It means that we have 0, 1, 2, 3, so discrete. We can countable. We can count stochastic one by one. But in general version of a stochastic period, stochastic process, that can be a continuous time, continuous process. You know, time is continuous, right? Time is continuous. 1 minute, 2 minutes is discrete, but it is arbitrary. Our human partition of the time, but time itself is continuous. So therefore, we can make this subscript continuous, actually. So that we have continuous version of stochastic process, which we deal with it later on. But for the time being, let's focus on discrete stochastic process. So we have two stochastic process, and then we say xn is martingale with respect to yn if it satisfies these two conditions. First, again, integrability condition, we can do the integration. And second, your best guess, xn plus 1, given the information y is just xn. What you can observe right now. Okay. This is slightly more. So first one is special case of second one, right? So this is slightly more generalized definition of slightly more general definition of martingale. So xn is, if we satisfy these two conditions, xn is a martingale with respect to yn. Okay. So it is useful. So what this y0 yn mean? It means it is useful to think of the stochastic process, history of a stochastic process of yn up to n. On the information, you can regard this one as information. On the information or history of the time or stage n. By the way, about this integrability condition, couple of years ago, I did interview for new undergraduate student. You know, what is that? 입학 사정관. something like that in Korean. I don't know how can I say that in English. What is 입학사정관 in English? Anyway, in Korean university, what? Yeah, in Korean universities, when you accept a new, fresh university student, there are several ways to recruit new students. Like they can take exam and they apply and we pick the top 30, something like that. Alternatively, and another set of students comes from by interviewing them. And I was an interviewer. I was interviewer for the new student. And then I asked students like that, did you learn probability and statistics? And students say, yes, we learned probability and statistics. And I also asked, did you learn calculus, like differentiation, integration? And students say, yes, we learned differentiation and integration. And I asked, why integration is important in statistics? I asked that, and surprisingly, not many students cannot answer. Not many candidates could not answer that question. They know integration and differentiation, and they learned probability and statistics, but they don't know why integration is important in probability and statistics. It is important because we define expectation or probability with integration. You know, in high school, is standard normal distribution. Do you remember? Like if we have a normal distribution is looks like this, right? Like normal distribution is looks like this, right? And then this is A and this is B, and probability that some event happen, right, between A and B, random variable is realized between A and B is the size of this area, right? And how we can get the size of this area? By simply doing integration of this probability density function on the area between A and B. This is a probability of event happening in this region. Right? So that's why integration is very important in statistics and probability. But surprisingly, not many students could not answer this question. But anyway, yeah. This is integrability condition and its definition. Now the history determines xn in the sense that xn is a function of y0 to yn. In other words, i.e., knowledge of the value of y0 to yn determines the value of xn. Okay. This is a blank page, like this. And then about this is like, you know, this is the obvious, right? This is obvious because xn is in the history of this one, so expectation of xn given the information of this one is simply xn because we already know xn. And then another one is now we can derive unconditional expectation of a stochastic process. If a stochastic process is martingale, each random variable in stochastic process should all have the same mean, same expectation because of a law of iterative expectation. For example, expectation of xn plus 1 is, because it is martingale, we can write down using the law of iterative expectation. We can write this one as e of e xn plus 1 given y0 and expectation. You can write this one. But we know this is simply xn because it's martingale, therefore this is the same to this one. About the law, so from this stage to this stage, we use the law of iterative expectation. To refresh your memory, the law of iterative expectation means that if G is a subset of H, then expectation of X given this small information is same to this small set is same to expectation of x given larger set and given g. Sorry, this is small g, same small g. And we can interpret this small g and this g and h as information. So h is larger information. H, there is more information in h and there is smaller information in g. So if you calculate expectation of x given small information, then it is like you first get the expectation given the large expectation, and then you calculate conditional expectation with smaller information. So it means that you assume you have a larger information set h and you get the expectation, and then take expectation with the conditional expectation with smaller information, and they are same. Which means that smaller information always win. Okay. So that's intuition. Did you learn this law of iterative expectation in other class? No? No. Anyway, this is important one. If you are more interested, this is very important one. So if you are interested in this law of iterative expectation, you can just Google it, and there are full discussion about this. But I mean, it should be intuitively appealing. You have small information and large information. I mean, if you have more information, so you can get a better estimate of a random variable, better estimate of something, right? With smaller information, you have a cruder estimate of something, right? So if you have small information and large information, and if you do the conditional expectation of small and large, then eventually smaller information wins, because you cannot get over the small information, because in the end we have only small information. So that is the intuition. Now, sum of independent random variable. Suppose let's define y0 is simply 0, and then y1, y2 be an independent random variable. Okay, so we have a new definition called independent random variable. What is independent random variable? What does it mean that two random variables are independent? What does it mean? Yes, what does it mean? This is I guess you all learned this one in high school and then introductory statistics class. By the way, in our Hanyang University PG school, do you learn statistics? Are you required to learn statistics? Did you learn statistics? Basic one? Okay, what is it? What we mean by two random variables are independent? A does not affect B. Okay. That's correct. That's correct. Yeah. But not 100% correct. Okay. So I assume you have an understanding about independence. So okay. Anyway, let's say they are all independent random variable, and then they all satisfy integrability condition. So absolute value, expectation of absolute value is all 0. And second condition is that the first one is 0. We know first one is 0. And second one, they are all random variables. So we don't exactly know the value, but its expectation is all 0. This is assumption. And then we define new random variable, such new random variable x, such that x0 is 0. And then we define new stochastic process such that xn is simply y1, sum of history of y up to n. So xn is y1 plus y2 plus yn for all n greater than or equal to 1. Then it is easy to check that xn is martingale with respect to yn. Right? So we can prove this. This is very easy. First, we check integrability condition. Expected value of absolute value should be less than infinity, and then its absolute value is this one, and it should be less than equal to sum of individual absolute value, and each one is, by this assumption, where is it? they are all less than infinity, so sum is all less than infinity. Done. Second one, more important one. Now we have to prove that expectation of xn plus 1 given the history of y should be equal to xn. We have to show that. And then we can decompose xn plus 1 into xn plus yn plus 1. Now, again, expectation is simply integration. In calculus is basically linear operator, right? So we can decompose sum into two parts, right? Because it is integration, right? So expectation of xn plus yn plus 1 can be separated, can be decomposed because it is integration, right? So xn, give the history of this one, but we know xn because it is in the information set. So it is simply xn. So we don't need, we can get rid of this expectation. We know exact value of xn. But second one is, well, same to this one. Why? Why we suddenly can, why we don't have this one? Why do we have from here to here? Why? Why I suddenly removed this one? Why? Because they are independent. Yeah? Yes, exactly. They are independent. You described it, right? So by the assumption of independence, it doesn't matter, right? This information is independent of this realization of yn plus 1. We can get rid of it, this one. And then what? Expectation of yn plus 1 is 0, so xn. So we show that this one is the same to this one, right? So we show that it is martingale. Done. It is fun, isn't it? Not fun. It's so easy, isn't it? Yeah. So you can regard again xn as stock price and yn is like a change of stock price, right? Like we can set initial stock price 0, and then like change of stock price. So at the beginning of the market, change of stock price is 0, right? Starting opening price, and each change of, if we sum change of stock price, it is stock price of today, stock price at a particular time. But if market is efficient, each change of stock price should be independent of each other, right? And so we can interpret this or something like that. Another one is the variance of a sum is also martingale. Again, we have y01 and we can define y1, y2 be independent and identically. Now it is not only independent, but also they are identically distributed random variables. It means that they are drawn from the same distribution. So probability distribution doesn't change. We draw sample, random sample from the exact same distribution. So identically distributed, independent and identically distributed random variable, such that they are drawn from identical distribution, so their mean and variance should be same if they exist. Of course, for some probability distribution, we cannot define mean and variance, like a t distribution. There is no mean and variance in the t distribution. But here, at least we have mean and variance. So they are identical, so they have the same mean and variance, and mean is 0, and variance is all sigma square for all stochastic process, for all random variable in the stochastic process. Yeah? And then we define new random variable xi such that x0 is 0, and we define xn as sum of y square minus n sigma square, something like this. And this is also martingale. Okay, sum of square minus n sigma square. Okay. So this is martingale, and then you can show it. Again, we can check integrability condition, and then second, we have to show xn given the history of yn we have to show this should be equal to this one, and then this is slightly messier. We can write down xn plus 1 like this one, and then we can solve these square terms and like this one, and we decompose into two parts, and this is sigma square 0, so xn minus sigma square done. It is doable, so it is easy. So therefore xn is martingale with respect to yn. Okay. Any question? Good. Now, another very important Doops martingale process. So, let's define y0, y1, this stochastic process y be an arbitrary sequence. So, it is arbitrary. It can be any sequence. It is arbitrary sequence, random variable. And suppose there is x. X is a random variable. And then we know random variable, this random variable is integrable. And then we define xn. Okay? If we define xn as conditional expectation of x given the history of yn, then xn is martingale. So x is something, okay? There is some random variable, and we define new random variable xn as its conditional expectation, and that conditional expectation is martingale. This is also very intuitive. This is mathematically intuitive, but we want to find financial, economic, and finance intuition about this one. So we can think x, this mysterious x, as some fair stock price, maybe true stock price, only God knows, right? You know, those stock analysts in the investment bank, they argue they know stock price, right? But interestingly, they have all difference of opinions, right? But anyway, the true fair stock price, value of the company, true value of the Apple, possibly, only God knows about this. Okay, what we observe in the market, there is market price that can be different from true fair price if it exists, right? And then the market price is somehow markets conditional information, right? Conditional expectation. We can interpret stock price of Apple today as conditional expectation of true hidden value of the Apple given the history of information, given the information we accumulated until now. Right? We can interpret Apple stock price like this. And if market is efficient, that stock price should be a martingale. Right? Right? So again, X is, you can look at the true fair stock price, and Xn is the observed stock price given the history of information, given the information set up to n. And that is martingale. It is again, we can prove this one. First, we can check integrability condition. Expectation of absolute value of xn is simply this one, and this is simply less than this one. We can put absolute value inside of this one, and it should be less than equal to this one because it is integration. Absolute value of integration is always less than equal to absolute integration of absolute value, right? So therefore, we have this one, right? I mean, this term is basically, this part is because this part basically means that, again, you know, f dx in integration, this one should be less than equal to integration of f, right? This statement, simply this statement. So anyway, this one, so well, we know this is less than infinity, so yeah, low iterative expectation, so integrability condition hold. Second one, we have to show this exn plus 1 is same to xn, but this xn plus 1 definition of xn plus 1 is this one, we can put this one over here, so it is ex over expectation up to yn plus 1. But so it is expectation if we have information up to yn plus 1, but in the end we have information only up to yn, therefore low iterative expectation, small information wins, so we get rid of this one, the expectation only up to yn, so it is xn, done. So why stock price is martingale? Because stock price is, in the short term, why stock price is martingale? Because stock price is conditional expectation of all the information available up to now. So because of this Dupes martingale process, stochastic Dupes martingale process, therefore stock price should be martingale in the short term. Because stock price is conditional expectation. Right? This is intuitive, isn't it? Very intuitive, right? By the way, if you have any question, please stop me and ask it. I want this class interactive, not unilateral. It should be bilateral, and we have to have a discussion a lot, and that's what I think of good education. So please stop me and express your opinion or feedback or question or anything. Do you have any thought about this one? Do you have any question? Oh, you want me to slow down? Okay, too fast. So it is you. You have to slow me down. Okay. Yeah, I don't know. I mean, I think I'm slow enough. Yeah. So, but you think it is not. Some of you think it is not. So please slow me down. Okay. Any other question? Yeah. 뭐 어떤 부분이 너무 빠른 것 같아? Which part is too fast? Oh, really? So now you have understanding? Okay. Yeah. You look very happy. Any question? You're very happy to learn new knowledge and acquire happiness of acquiring new knowledge and then enlightenment. Okay, I'm joking. Yeah. Okay, let's move to next one. Now we have a very exciting topic. Okay, probability space. This is the most popular way, at least in university, most popular way of defining probability. Okay, what is the probability? How did you learn the probability? What is the definition of probability you learned? What is your name? Huh? 유동열? 연? 유동연. What is probability? What is probability? Where are you from? Germany. Germany. What is the German definition of probability? Likelihood event. Okay, then what is likelihood? Okay. Okay. What's your name? What is the definition of probability? 우리말로, if you think it is too hard to describe in English, you can use Korean. Then I will translate for other students. Measure of likeliness. What is likeliness? Okay, chance of something happening. Then what do you mean by chance? percentage. So percent of what? Percent of something happening. Okay, that's the probability. Okay. No, that is kind of totally then how do we measure percent of something happening? How we can define the percent of something happening? Again or again. Okay. How many we have to try again and again? How many times? 100 times or over 30? Yes, 30 is a magic number in some case. So I mean, the definition of probability. Again, several years ago, 2 years ago and 3 years ago, there is another way of entering Hanyang University as a new student. Hanyang University developed our own exam, and students take that exam. And if their score is good and they can come to Hanyang University, we admit him or her as Hanyang University new student. And then I was one of the professors who developed mathematical problems for 상경계 입시, our business school new student. And then therefore, I have to go over high school textbook. And I was especially interested in high school textbook about probability and statistics. And I was very surprised. Only one, I go over like 10 high school textbook, and only one textbook describes the definition of probability. Only one. 신사고. The publisher name was 신사고. He's a Korean publisher. Only one textbook exactly define probability. None of them define probability. They explain things, topics, advanced topics without explaining probability. That's very weird. So anyway, we will now exactly determine probability and random variable, those things. Like in the high school textbook, we all learned random variable, right? 확률 변수, random variable. But none of high school textbooks define random variable well. I don't mean the mathematical rigorous definition like this, but no, even the intuitive definition, they don't describe it well. So I was very unhappy with high school textbooks. Anyway, yeah. So I will introduce what we mean by random variable, what we mean by probability, what we mean by event, or those things. And this is very most popular way of defining those probability and related concept. It is developed by Kolmogorov. Have you ever heard of Kolmogorov? One of the great mathematician and statistician. Okay, martingale with the sigma field. Okay, first we have to define probability space. When we say probability space, it is like this triplet. We have three things: omega, f, p. Okay, omega, f, p. First, what is omega? Omega is a sample space. It is called sample space. It is a sample space, a set. So it is a set. Okay, it is set. A set omega, and then it has an element whose element is small omega, correspond to possible outcomes of an experiment. So it is possible outcomes of experiments. So omega is again a set, its element is a possible outcome of an experiment. Experiment means like throwing coin or throwing dice, something like that. If we throw coin one time, what is the possible outcome? Yeah, head or tail. If we roll the dice, possible outcome is 1, 2, 3, 4, 5, 6. So in that case, if we throw, no, not we can throw. If we throw coin, we toss coin. If we toss coin, the omega is set whose element is head, tail, HT. If we roll a dice, then omega is a set, its element is 1, 2, 3, 4, 5, 6. Okay? And the second, event. Okay, probability is defined on event, right? Event, probability of some event, right? probability not defined on sample space. It is defined on event. And event means a family of event is a collection of subset A of omega. Okay? So there is a subset of omega. Okay? Omega is a sample size. So basically event means subset of omega. Okay? And actually family of those subset, collection of subset. So we say an event A occurs. Okay? So if we define the probability of something, that something is actually event. And what we mean by an event happens, it means that event A occurs means if outcome of omega belongs to A, then we can say an event happened. So for example, in case of, suppose we roll the dice. If we roll the dice, then omega is 0. No, not 0. 0 is not possible. 1, 2, 3, 4, 5, 6, right? This is too small. Right? So this is omega. And an event, we can define an event. And there are many possible events that can happen. Suppose if we define A as a, we can define A as 1, 3, 5. Okay, in this sample space, so A is a subset of this sample space, right? This is subset. And what does A mean? If we say A happens, what it usually means? Right? What is 1, 3, 5? What is the common property of 1, 3, 5? It is odd number, right? So when we roll the dice and we say event A happened, it means that oh, if I roll the dice, it is the event that odd number happens, right? So when we roll the dice, an event of odd number happening means an element, which is this one of this one, is whether in A or not. If we roll the dice and 6 is not here, so we say, oh, A didn't happen, which means odd number didn't happen, right? When we roll the dice and we have 3, then 3 is in the sample space and in A, a particular subset of omega, which is A. We can say, oh, A happened. It means that odd number happens, right? And there are all possible subsets. Subset of 2, 4, 6 is the event of happening odd number, right? Something like that. And we can define any subset, right? Like this. So this family of subsets is called event. Okay? Okay? The family of events. Okay, it's a family of events. And family is a particular subset. And if we collect those events, it is a family of events. And we can define probability over this event. Right? So if we define A, So anyway, if we define A, then we can say, now define P. P over this particular subset. If dice is fair, then if A is odd number, it is 1/2, right? Something like that. And the probability, this is the definition of probability. Okay? The third one is less technical, but probability of that. First, this probability is always between 0 and 1. Okay? You know, probability cannot be, probability is 2. It doesn't make sense. Probability is -3. It's not possible because it's against the definition of probability, and probability is always between 0 and 1. And actually probability is also a function. Okay? Probability function defined on these events, family of events. So it is a function from a set to the real number, right? Probability A, probability odd number, probability of odd number 1/2. Odd number, it is set, possible set, right? So it is a set function. It is a function defined on a possible set. And then its function, the value of a function is always 0 and 1. And value of nothing happens, not happening, right, is 0. And probability of something happens is 1. So if we roll the dice, and probability of either 1, 2, 3, 4, 5, 6 is 1, right? And if we roll the dice, probability of -2, 0, right? That's right there. Okay. And then another one is that now union, we have two sets A1, A2. Probability of either A1 and A2 happening is probability A1 plus probability A2 minus PA1 subset A2. Okay, so this is the second one. Third one is some countable sum. So this is infinity. You can disregard the infinity for the timing, but if we add event in a countable way, and each event is disjoint, mutually disjoint, which means that intersection is null set, then union is simply sum of the probability. Probability of union is sum of the probability if those events are disjoint. Probability of 1, 2, and 3, 4, right? 1, 2, probability 1, 2 happening, probability of 3, 4 happening. Well, 1, 2 happening and 3, 4 happening, they are mutually disjoint, right? Therefore, we can simply add probability of 1, 2, 3, 4 happening is simply, if it is really probability, it should be same to probability 1, 2, and probability 3, 4. So if a function defined on a set satisfies these three probability, we say this one as probability. These three properties, it is probability. So exact definition of probability is like this. So when we say probability space, we have three things, right? First, sample space. Second one is family of events, and we define this probability measure, probability function on this F, collection of events. This calls probability triplet or probability space. This is very important. Any question? 질문 있어요? I mean, you can ask question with any language that I can understand, which means only Korean and English. No, you can ask question in English or Korean as you want. Any question? This is very, very important. Okay, I will show you an example. I will toss a coin. If we toss the coin, then omega is what? If we toss the coin, omega is what? Omega is sample space. What is the sample space of tossing a coin? Yes, head or tail, H or T. Then what is the sample? What is the event, family of event? Well, it depends on what kind of information you have. Okay, so in this case, let's define event, family of events. So let's define this F, family of event, as a power set of omega. What I mean by power set of omega, power set means all possible subset we can generate with omega. I think you learned this one in high school. What is the number of all possible subset of this omega? Did you learn? What is the number of all subset of the omega? epsilon? What is the number? How many subsets do we have? How many subsets can we generate with this omega? How many? 4. Why? That's true. So sometimes it is another notation of this power set. Sometimes we write down this way also. 2 to the power of omega. And then this number of this power set. Okay? Or, I mean, it's the same way. Number of these 2 omega is simply, in this case, 4. Okay? Why? I mean, it is easy, right? We can generate a subset, so there is somewhere we can put either this one in or out. We can make this one in or out. So we have 4 possible combinations. So we have 4. So this is 2 in and out, 2, and it can be called in and out, 2 multiplied 2, 4. In case if we roll the dice, all number of possible subset is 2 to the power of 6, because each number can happen or not, something like that. When we generate a subset, right? So that's why we have 2 to the power of number of subsets. So when we say power set, it means all possible subsets. So in this case, 4. So in this case, in this particular example, I have family of event which is all power set of the sample space, all possible subset, and then I can define. Okay. In this case, my probability function of such that, because I have to define when I say probability, I have to define probability not on omega. I have to define probability in the F, right? Family of event. So my definition of probability, this one is, I say 0, and probability this one of this omega. Omega is a subset of omega, right? This is 1. And what is a possible subset is, now we have to just set H. This is one possible subset, right? And I can define this one as 1/2. And then I can define T as 1/2. Okay? They're all subset. And then we have 1, 2, 3, 4. 4 subset, and we define, and I define probability all the possible events. So this one. This is the probability space of tossing a fair coin. It is fair coin, right? Because it is same probability. It's the probability space of tossing a fair coin only 1 time. If we draw coin 2 times, well, probability space would be more complicated. Right? If we draw coin 2 times, what is the sample space? If we toss the coin 2 times, what is the sample space? Now sample space HH, HT, TH, TT, right? And all possible subset power set is, we have 2 to the, so for 16 subsets. And then in order to define probability, I have to define this probability in all possible 16 1. Of course, if we are drawing fair coin, we can mathematically generate those things. If it is a fair and independent trial, we can mathematically generate those numbers, probability. That's not difficult, right? But anyway, so do you understand what so this is very important. Any question? Any question about this probability space thing? Any question? 질문 있어요? What is your name? 김국인. Do you have a question? It's all too easy. Right? Not easy, then why it is not easy? There is something you make only. Which part is not easy? So which part specifically?
It's for lower time. I understand for watching
예. 얘는 어렵나? Bill, do you have a question? No. Okay, martingale is random variable, right? Martingale is special property of a series of random variable. We didn't define random variable yet. Okay.
The special property is that expectation value of n. So it's the same as xn.
So expectation of xn plus 1 given the information up to n is the same to xn. That is martingale. Yeah. But here this x thing are random variable, and we didn't define random variable yet. Right? That's something I think it is slower than I expected, but I think we can learn what we mean by random variable next class. But anyway, we have to learn now sigma field. What is these horrible notations? Wow, this is a very horrible notation, right? Sigma field. Okay, sigma field means that about this family of event. I said family of event, right? And in my example, tossing a coin to this family of event, I define this family event as a power set of the sample space, right? Power set of it is okay in this case. Power set of sample space okay. It might have been, but I mean, if we don't have full information of something, or sometimes in case of real number for mathematical reason, it is not always possible to define probability on power set. So in any case, anyway, when we define these events, okay, probability is defined on event, right? And about these event things, not everything can become an event. When we define this family of event, we have to give them some structure. If we don't give structure, we can define probability. Okay? How can we say mathematically or intuitively? Basically, in the probability is basically measuring some amount, right? Because I mean, we have a sample space, and in sample space there are slice of subset. So this event is a slice of sample space, right? And the probability of that sample space, no. So we have a sample space and a particular event. Event is a slice of sample space, right? And we assign number to the slice of sample space, which is event. So probability is actually measure amount of the event. So it is like this. Suppose we have snow on the Hanyang University campus. Okay? So we have snow in Hanyang University campus, and we normalize total amount of snow in the campus as 1. Okay? And then a special part of the snow in front of business school, that is a subset of the snow in Hanyang University. And that amount of snow is probability of the snow in front of Hanyang University. We can define it like that. So basically, probability is amount of something. So this event, so in order to measure the amount of snow, again, total amount of snow in Hanyang University, which we regard as sample space, total amount of snow we can normalize as 1, and we are interested in the amount of snow because the total amount is 1, which is 100%. So slice of snow in front of business school, in front of law school, is like a percent of snow in some sense, right? So we are interested in the amount. But that event, the slice, when in order to measure snow in front of business school, law school, anywhere, and the slice should be clean, right? If slice is a rectangle, it is fine. Slice is round shape, it is fine. We can measure that. But if we do the slice very weird way, we can put slice in Cantor said something. Anyway, if we put a slice in very weird way, some mathematical weird way, maybe it is impossible to measure snow, possibly. Okay, so in order to measure the amount of snow, okay, we have to give some structure of slicing the snow in Hanyang University. And the question is, how we can slice the snow? What is the restriction, minimal restriction of slicing the snow in the Hanyang University, right? That is our question. And that minimum restriction, the rule of slicing snow in Hanyang University, that rule is called sigma field. We have to slice snow in Hanyang University in a way corresponding to sigma field. As far as we can slice snow on the sigma field, we can measure the amount of snows. Okay, so sigma field is the rule of slicing snow. And then the sigma field, the rule of the slicing the snow is like this, which is kind of horrible, looks horrible and complicated, but it is actually very, very intuitive. First, if we have a slice, so this F is possible way of slicing the snow. So suppose we have a slice of something, okay? Then if we get rid of that slice, the remaining part should be also slice of snow, right? So if we separate our snow in front of business school, we have snow except snow outside of business school, right? So if a slice is in the collection, its complement should be also in slice. So if this property is not satisfied, this is very weird slice, right? Something it is hard to imagine, right? Every usual, ordinary slice will satisfy this one anyway, right? This is very natural. Second one is that, okay, if A1, okay, well, time's up, so see you next week. See you next Wednesday. I don't think I can explain this one in 1 minute. So, okay, any question until now, today? No, it is a very exciting topic, isn't it? Have you ever learned probability in this way before? No? No? Okay. Good. See you next Wednesday.